Hey, welcome to this week's episode of the Structural Engineering Podcast. My name is Max.
And I'm Zach.
And this week, we're talking with Kevin Lamalva about performance-based fire design.
This week's episode, we kind of go into it, but we don't go into it too far. We don't really go into the nitty-gritty. I really like this one, Max.
After last week's Intro to Fire episode, we reached out to one of the most informed structural engineers we know, and we've had him on the show before, and asked him what he thought some of the most important things are for a structural engineer to know about fire design. He gave us a list of 7. Here they are.
Combustion and fire-rated buildings are required to be smaller than their construction type due to the level of risk associated with a fire in that building.
Also, construction type, Table 601, has everything to do with protecting the actual structural members of the building from fire, and pretty much nothing to do with fire spread resistance.
There are 5 types of fire or smoke separation walls described in the IBC in 706 through 710. Anything that is properly a firewall gets to be a little intense. Firewalls shall be designed and constructed to allow collapse of the structure on either side without collapse of the wall under fire conditions. This type of rationale does not apply to any other assembly or type of thing. A firewall gives the architect more flexibility but can be difficult to construct unless you use 2 walls.
Read 3 code sections. These are IBC section 704.3, 704.4, and 704.4.1. The 0.4.1 underwent a change in the 2018 IBC to try to clarify it a bit. The term individual encasement protection really means surrounding the member on all sides with fire-rated stuff, usually chipboard. That can be pretty expensive. To make it cheaper, if you can hide the member, let's say above a ceiling cavity that's already going to be covered with chipboard, or within a wall that'll be covered with chip, regardless, you can reduce the price.
Most fire-rated assemblies come from the IBC section 703.3, item 1 and item 6. These say that an agency has conducted fire tests and lists exactly how you have to build something to make it fire rated. These rarely, but sometimes include restrictions on structural loading. There's an evaluation reports that also have these in them with structural loading restrictions.
Stairways are very special and concerning for fire spread. People need them to get out during a fire. You essentially can't penetrate their surrounding walls in most any fashion. There's contention around whether structural members can even penetrate these walls. Be certain the structure penetrating the stairway walls is necessary for supporting the walls. Along the same lines, absolutely do not assume you can platform frame into these walls.
Most everything fire rated is required to be supported by stuff that is fire rated. Supported by is intended to only invoke gravity load path. The supported by thing invokes a lot more thought amongst us structural engineers than it does to the architects.
There you have it. That's what a structural plans reviewer thinks you should know about fire design as it relates to structural engineering. Now, without further ado, let's get into the full episode with Kevin.
Kevin, thank you so much for being on the show this week. We're really excited to talk about performance-based structural fire design. Before we get into that, could you tell us a little bit about yourself, who you are, and a bit about your background?
Sure. So I'd say above all, I consider myself to be a passionate advocate of structural fire safety. So that's sort of my core mission that I sort of take with me from endeavor to endeavor. I always knew I wanted to be a structural engineer dating back to probably days in high school. But when I was in high school, the tragic events of 9/11 happened, and it sort of made me scratch my head of fire effects on structures, and I developed an interest in fire protection as well. So I attended Worcester Polytechnic Institute. I got my undergrad in structural engineering and my master's degree in fire protection engineering. I was fortunate enough to have some really good mentors that sort of custom made a curriculum for me that blended structural engineering with fire protection engineering.
When you were in school, structural fire engineering, what umbrella program was that under? I've never seen this at a university. Is that still in the civil category?
WPI has a fire protection engineering program.
Wow.
And there's other schools that, it's not as common as civil, but there are other universities like the University of Maryland, UCal Berkeley, that have fire protection engineering. And that discipline has a wide sort of bandwidth. Some people go into sprinkler system design. Some people go into fire alarm design. Some people go into smoke control systems. And structural fire protection is a small sort of slice of that. It really wasn't a structural fire engineering curriculum, but as we might get to in our discussion, that's changing. The American Society of Civil Engineers, for instance, their Futures Fund, part of the initiative this year is to develop more curriculum in structural fire engineering. And there are some universities that currently teach it. It's a very niche thing, but we're trying to further expand it.
You may be thinking, why do we need this? We've got sprinkler systems, intumescent paint and cementitious spray. We've had systems like this for over 100 years. Surely they've been refined and perfected over that time, right? I asked Kevin, what's the purpose of performance-based fire? What's the need?
It's a question that I pose in a lot of presentations I do. One of my first slides, I pose the question, why do we thermally insulate structures? And, what's the sort of core purpose of that? Fire sprinkler systems are pretty ubiquitous in engineered buildings, and they're really good at putting a fire out when it's in its incipient phases, so after it's just ignited. But one common misconception about sprinkler systems is it's not like what you see in the movies where the character will sort of put a lighter to a single sprinkler head and then it's basically all the sprinkler heads going off at once. Sprinkler systems aren't designed that way, and I've actually partaken in such designs. Hydraulically, they're only designed for a handful of contiguous sprinkler heads to actuate, maybe a maximum of 6, only in the area where a fire could occur, and that could be anywhere. But if you ever look above the, poke up this drop ceiling and take a look above, the branch pipe in a sprinkler systems is pretty small. They're only, maybe an inch piping. So there's only so much water that you can be delivering to a fire. So sprinkler systems, their effectiveness drops precipitously when the number of sprinkler heads that actuate goes beyond the design intent. So if you have an extraordinary event, it could be something as simple as a fire happening in 2 locations at the same time, or just a really big fire, say due to an explosion. You can have a case where the sprinkler system's not effective at controlling the fire. Also, at the same time, there's going to be firefighter response, but their ability to control the fire may be hindered by some logistical aspects. For instance, if it's a high-rise building, their aerial hose ladders can only go so high to spray from the outside. From the inside, the way that they put it out is they carry these super heavy hoses up stairways, multiple floors to get to whatever the fire floor is. Then they hook their hose into what's called a standpipe connection. So if you're ever in a stairwell and you see a big pipe with a connection, they hook their hoses to that, and then they start fighting the fire from their staging, which would be in the stairwell. So the stairwell is a place where the building code precludes you from having combustibles. You can't just store trash bags and things in the stairwell. So it needs to be a sterile, safe place that firefighters and occupants can utilize for in an emergency. So all of those aspects, there may be cases where you have an uncontrolled fire. And when you have an uncontrolled fire, the intrinsic safety of the structure is relied upon, not just for occupant and firefighter life safety, but also for just the overall resilience of the building. And when a structure is heated, the first thing is it tries to expand. So like a steel beam will increase in length as it's heated, and when it's cooled, it will contract. So that is sort of there'll be a set of forces and rotations throughout the fire that the structure needs to endure. And at the same time, as certain structural materials are heated, their material properties change. Predominantly, the yield strength will go down and the stiffness of the structure will go down. So you'll have large deflections. Now, a structure that is robust under ambient loads, so the way we traditionally design structures for seismic motions and winds, one of those two will probably control. For lateral loads, gravity, live, a robust structure in ambient is not necessarily robust under fire. So that is really the intent of structural fire protection. And thermally insulating members is one way to reduce temperatures. But, as we'll probably get into a little bit, that's no assurance that it's going to perform how you want.
To give some context on what type of fire risk we have in the U.S., reports from FEMA show that in 2018, we had 1.3 million structure fires, costing $25.6 billion in damage and 3,500 lives.
One thing that kind of hit me also when you're talking with all this performance-based structural fire design, we're going to definitely get into that a lot more. Is it only looking towards maybe steel structures, or is this going towards everything, wood, masonry, concrete, and steel?
I would say it definitely can encompass them all. However, fire has always been, I'll put it kind of like an Achilles heel to steel structures, because steel by itself can quickly lose its ambient properties as it's heated. So the steel industry and affiliates over the decades, out of necessity, from my view, have invested a lot of research into the fire safety of steel structures. So we'll get into some guides and things that are out there. And the meat of the sort of knowledge database is in steel structures, but concrete is probably close behind in terms of understanding how they perform at elevated temperatures. So we have, I would say at the current day, we have a good grounding in how to analyze a steel structure, then followed by concrete. And I would probably put timber last. Timber is something that is come onto the scene in terms of performance-based fire more recently. And there's some key knowledge gaps that can certainly be filled. It's just a matter of getting the data and the research.
No, I think that makes a lot of sense. Max and I are both structural engineers, and as you know, with our clients, everything we're doing, we're chasing this code level design. So where in code does fire resistance, where is it discussed?
Yeah, absolutely. That's a great question, because one thing I'll say from the start is, as a structural engineer, if you're not familiar with fire resistance, there's no shame in that, because the code does not require the participation of a structural engineer in prescriptive structural fire protection. And the way that the code, in terms of its prescriptive basis, exists today is very similar to how it was a century ago. It's essentially, when you look in Chapter 6 of, say, the International Building Code, there's a table there that basically divides a building into one of 5 construction types. So type 1, 2, 3, 4, 5. A type 1 building is going to be non-combustible. A type 1 and 2 is non-combustible construction. A type 3 is non-combustible interior construction, but combustible interior construction, but the exterior walls need to be non-combustible. Type 4 is heavy timber, and type 5 is lightweight timber, or it could be anything you want. And based upon those construction types, it prescribes the hourly rating that individual structural elements need. So say you have a type 2 building or a type 1, and the code for your construction types states that columns need to be 2-hour rated or perhaps 3-hour rated. Then you basically open up the Underwriters Laboratory's fire resistance directory, and you find a fire protection or fireproofing assembly for that column, for columns, that matches with that hourly rating.
I was actually going to ask, and it's tangential, but where that hourly rating came from, do you know sort of the root of that, and what the substance there is, why 1 hour and then jump to 2 hour?
Sure. If you wouldn't mind me sort of giving a little primer on what fire is, and then I'll lead into sort of what led to those individual hourly ratings. So fire resistance is entirely an artifact of furnace testing. And furnace testing's been pretty much relatively unchanged since 1918. So again, we're beyond the century mark. Witnessed this type of testing, and basically the furnace is 14 feet by 17 feet. They put a mock-up specimen, whether it be a single column or a single beam or a single floor, with no structural connections. So there's no continuity of structural system. And they just heat the living daylights out of it. And if it stays below certain thresholds of, say, mostly the temperature, say, of the steel element itself, but also they have a failure criterion where if the deflection looks too large and, oh crap, my furnace may get damaged, then they cut it off. And basically your hourly rating is how long it doesn't cross over those failure thresholds. So if your mock-up assembly lasts 2 hours and 5 minutes, you'll get a 2-hour rating. And you can test the same assembly 1,000 times, and if you pass once, then you get the hourly rating.
Wow.
So, if you look at these mock-ups, when the fireproofing is applied to this little mock-up, they'll bring in the most artisan fireproofing I've ever seen, and it looks majestic.
Perfect. Yeah.
Something that, it's hard to argue, or it's hard to argue that there's not a difference there between, what's in the field and what's in that test furnace. But, that's a sort of side tangent. And those hourly ratings essentially blanket a structure with fireproofing with the intent of limiting the temperature of the structure enough, quote unquote, enough to mitigate the risk of structural failure. So I'd like to relate that to what you guys do. I've heard that you do seismic design. That would be like if we base isolated every building, but we only did it partially. We didn't fully base isolate. We let seismic motion go into the structure to a certain extent, and we have no idea what the structure. We do no analysis of the structure above. So the way we blanket structures with fireproofing, we let them get pretty hot, and then we just say good. And as the base isolation analogy is, again, partial base isolation with no structural analysis. If you're into wind design, it's kind of like putting a encapsulating barrier around the structure, like a big wind wall, but they have these arbitrary holes in it that wind can hit through. But you don't analyze the structure. So what we end up with is the level of structural fire safety from structure to structure is contingent upon coincidental structural design decisions that are not based in fire, if it's going to be good or not. So the vulnerability of structures to structural failure due to fire is variable, not only based on geography, but just based upon building to building with different types of connections, for instance, or it's unknown. It's indeterminate when you do prescriptive design. Now, the hourly ratings back a century ago for high-risk buildings went all the way up to 4-hour ratings. So that is insulating the living hell out of a structural element. And the original intent was to insulate it so much that it heats so little that you wouldn't be too concerned about it. Although it is somewhat analogous to that partial base isolation because it's still getting heated. And the thing is, say, steel will expand pretty dramatically even at 200 centigrade. And if you just want some reference, the furnace test allows members to get up to 1300 Fahrenheit, whereas they could be, I'll stay in Fahrenheit, they can expand dramatically even at 400 Fahrenheit. So that's going to induce forces, and you don't know what's going to happen with that. Now, over time, and again, I have collaborators that are much better historians at this than me. But from what I understand, there's been sort of a whittling away of hourly ratings for different reasons. One is Sprinkler systems have become more common, and there's been sort of a trade-off in the code that if you put sprinkler systems, you can have less fire resistance. But again, I told you the design hazard is not, we're not trying to protect against a fire that's controlled by a sprinkler system, because that is trivial. It's not going to do anything in the structure. We're trying to protect against uncontrolled fire. So, there has been a historic decline in the fire resistance ratings that are required.
Interesting. In normal fire design, is there any accounting for the amount of fuel that might be available, or is this very generalized, like a residential is just this amount and industrial blanketed something else?
That's an excellent question. When we get into structural fire engineering, that's absolutely pertinent and absolutely essential.
Yeah.
Because that's the embryo of energy which heats your structure. In terms of the code, it's kind of indirect. So based in the construction type that you can have, I mentioned that if you build it taller or you build it bigger, it may push you into a certain construction type. Now, another thing that determines where those thresholds are from when you say go from type 3 to type 2 to type 1 is your occupancy. So there's different occupancies, like an assembly occupancy, a business occupancy, a high hazard occupancy. And those thresholds where you get tipped off into a higher construction type are lower for occupancies that are more hazardous generally. And generally, more hazardous a lot of times means more fuel energy. So that in the code is sort of a circuit breaker to prevent sort of high-rise fertilizer plants. You don't see those. The code kind of forces you out of them. But you see a high-rise office building because it sort of allows you to do that.
Yeah. Okay, so that kind of leads us into that. Tell us a little bit about performance-based fire design. Like at its root, what is it?
Absolutely. So it's sort of a movement in structural engineering, and myself and other people that are in this are grateful to the American Society of Civil Engineering, which is really helping to put it on a similar footing as performance-based seismic design and performance-based wind. We're trying to come up with earth, wind, and fire. So performance-based wind design, PBWD, performance-based seismic design, PBSD, and performance-based structural fire design, PBSFD. And we want those all to be conducted in the same rigor and oversight and prestige as each other. And the one that's sort of, way far beyond the other ones is performance-based seismic. That's been, really well developed. And, I've had mentors that have worked in that. And that is, we're the envy of performance-based, we're envious of what they've done. And, we're just trying to emulate that. Certainly also, I think ahead of us is performance-based wind. A pre-standard's been developed, and the infrastructure of that I think is more developed. Performance-based structural fire design is I would characterize it as in its infancy. And the way I would describe it is structural engineering for fire loads. So I mentioned the forces and rotations that are induced by fires. So the first step, as you alluded to, is to determine the amount of potential energy that you can have in a given space, which is the fuel load. The fuel load, which is combustibles, gets liberated with chemical reactions, thousands of chemical reactions in an instant, which is combustion. And that's an exothermic reaction that expels heat. So one way to think about a fire is it's a giant heat pump that's pumping heat. It's buoyant, so it's going to go up to the ceiling, it's going to spread, and it's going to sort of engulf your structure. And that's going to have a given temperature history. So at time X, you stick your hand up in that hot gas layer, it's going to be a certain temperature. Eventually, you're going to stick your hand up there, it's going to be like, it's pretty comfortable, because the fuel is finite. Unlike a furnace test, where they're basically just pumping in fuel and it just goes on forever, a actual fire will have a distinct growth phase, it will peak, and then it'll be fully developed where everything that can burn within a space is burning. And then as the fuel's depleted, it will decline, and you'll have a given sort of finite duration. Now, through that duration, the structure is expanding, it's losing strength, and it's also contracting. So it's the intelligent design for structural fire safety. So whereas the prescriptive method is entirely reliant on insulation, performance-based structural fire design basically uses insulation as necessary. That's on the demand side of the equation. But also, it gives you the ability to influence the capacity side. So, for instance, you can make targeted upgrades. They don't have to be substantial to, say, the slab mesh reinforcement and the connections, or the primary girder to column connections. And these can be readily implemented as part of suite design, so designing for your lateral loads, gravity, and fire, in order to allow for the safe deflection of floors without collapse. And you may be able to use a lot less fireproofing, or have a regime that is a lot better for your construction. And even the columns at the periphery of the structure, I mentioned that structures expand, so the floors are going to push out on exterior columns, which is going to introduce some eccentricity. That's another thing that can be upgraded. And, such measures, they can be from, you find that you don't need to make any changes because your coincidental structural design is actually robust, all the way to modest structural enhancements can dramatically raise the intrinsic safety and resilience of the structure compared to simply fireproofing the members. And, the $1 million question is, who's going to pay for that? One thing to think about is, how do we traditionally design structures? So we design for ambient loads. We have the structure, say the steel frame. Then we basically hand that off to an architect, and the architect just applies fireproofing to the whole structure. It may be surprising to structural engineers to know that fireproofing, in terms of material costs, if we're looking at just the steel frame, the fireproofing can account for 20% of the entire steel frame costs, with the steel tonnage being about 55%, and the core being about 15%. So the fireproofing can be more than the core of the building. Now, that is just the skeleton of the structure. Now, if we're talking about the core and shell, so pretty much the whole building cost, one thing that's humbling to structural engineers is the structure itself, is only maybe 12 to 15% of that whole building cost. About 60% is going to be your services and cladding. Now, within that 15% pie slice of what structural engineers can influence, fireproofing is about only 2%. What are we doing now? We're just sort of not even thinking about it, which is fine because the code does not require us as structural engineers to do that. However, what we're trying to motivate structural engineers to sort of extend their skills a little bit to go into this fire aspect is you can really have a big influence on the economics of the project. And what's your competition? Basically your competition is modern structural design mated with a century-old structural fire protection technology that is, quote unquote, cutting edge.
That's wild.
Yeah, it's like a wild dichotomy that it's. And the fire coatings and stuff that we see, like, how long has this been around, or in a fire protection like course or whatever, are we kind of just currently mostly teaching this? I guess the furnace is a 1918 test, but I assume it was like similar fire protection for the last 100 years.
Yeah, so the materials themselves have evolved. Back 100 years ago, and again, I'm not the best historian. It was more like a plaster material. Terracotta is a big one. But again, that plaster and terracotta is doing the same thing as a modern cementitious fireproofing. It's just acting as an insulator.
Yeah.
things that are a little more exotic and more expensive are intumescent paint. And the thing, people are usually sort of taken back by the price of intumescent paint when you apply it, because you have to blanket it across the whole building. But structural fire engineering can allow for you to target that paint to where you need it and actually allow for it to be applied offsite. So that sort of hindrance of your construction timeline of having to clear everyone out, basically bring in the bags of fireproofing and seal off the area and spray, that can be eliminated if it's engineered for. So there's, and again, structural fire engineering does not guarantee cost savings, but there are a lot of cases when it can really deliver a lot more efficiency. And it's not just the material cost. You're getting a better structure. You're getting a more resilient structure. If you're designing for floors to deflect safely, and we can actually design floors where they get stronger and stronger as they deflect. And I can go into a little the physics of that in a bit. But say you didn't design for, blast loads. If you're designing structures to be safe membranes and you have a column taken out for some reason, you may not have specifically designed for it, but it's even going to be more resilient to that because they're kind of related to each other. I meant that there's ways to save on carbon footprint, aesthetics. If you have exposed steel in a lot of cases, you can have more of it. And just a quality control, if you can set up an off-site applied coating targeted regime, the quality of that coating applied in the shop is going to be better than in the field. And, just the life cycle maintenance can be enhanced.
I saw in a presentation you gave, you guys did an example of I think it was just a 6-story building and either using performance-based fire design or without, and some of the benefits. And the one you mentioned that I remember seeing is this targeted application of intumescent paint, right? What, in that example, what else did you see cost-wise and total structure weight and stuff? What was the outcome of that?
Sure. Yeah. So we looked at first the what I'll call the spray and pray method, which is prescriptive, where basically all the members are just insulated with no structural upgrades. So basically, we took the anatomatized structural design, which was controlled by wind for lateral, but in gravity, and we ran a fragility study where instead of the ground motion being increased for seismic design, we were increasing the fuel load from a conceivable to a nearly inconceivable level. And what we found with that basically nominal structural design that sprayed everywhere with traditional fireproofing on site is that it actually wasn't very, it was quite fragile to the fire. It didn't take a lot of increase in fuel load to result in a condition that we felt was precarious and may or may not collapse. Then we sort of took from that what we understood about the potential vulnerabilities of the structural system, and we zeroed in on the density of the welded wire mesh in the slab, its positioning within the slab, and granted that welded wire mesh is there for serviceability, shrinkage, crackage consideration. So what we made, one thing about structural fire design that's important is you can't tweak the structure that's going to then invalidate other objectives for ambient load. So for example, when we were playing with the density and elevation of the welded wire fabric within the slab, we made sure that we were still upholding the serviceability intent. Another thing was the connections between the primary members and the columns. We had to do some modest enhancements there, which when I say modest, increase in the bolt hole edge distance by a quarter inch or so, and just on some of them maybe adding a bolt. So nothing crazy. We're not converting a shared connection to a moment connection. And when we did that, and we had the floor beams unprotected, so the secondary beams were unprotected. The primary beams we had protected, but only protected to an extent that we needed. So we didn't just put on the full thickness. We actually got away with what might be the deciding factor between if you have to go with an epoxy intumescent or a thin film intumescent. So a thin film intumescent is going to look better. It's going to be thinner. You can apply it in the shop and it won't be damaged during transport. So the thickness of your intumescent, as that goes up, its susceptibility to damage on a truck bed goes up exponentially. So fine-tuning all of those variables to come up with a construction regime that eliminates the wet trade from your construction. We found that floor design, it gets stronger as it deflects, and it becomes much more robust. It's able to take much higher fuel loads. It's much safer. And the way that it sort of becomes stronger is it's almost designed like a bicycle wheel. So if you take a bicycle wheel and you hold it horizontally, you push down on the center hub, it actually gets stronger as you push down on it. And what's happening there is you're having a self-equilibrated set of forces. So you're having the spokes go into tension, the rim is going into compression. They're counterbalancing each other. As you push further down, the rim goes into more compression. Now, what's a coincidental good thing about a steel slab design? We always over-design the concrete compressive stress block because we want it to fail in tension. So we don't need to increase the thickness of the slab to be able to take a lot of compression there. We needed to increase the density of the mesh a little bit. Now, we're not increasing the mesh to something where it's basically just crossing rebar. It didn't take a lot of enhancement there. But we ended up with a much better system and, much safer. So what we were able to do with that, and again, this is hypothetical, and this was conducted within a research project that was sponsored by the Charles Pankow Foundation in conjunction with the Structural Engineering Institute. And I can go a little bit into the background of that. So it's a hypothetical, and we found that just those aspects of optimizing the structure with the applied fire protection could shave about 5 weeks off of the construction of the building. And the benefit of that is a function of how speculative your building is, how complex the site conditions are. So performance-based structural fire design, as I said, it's not a guarantee of results, but of economic benefit. It's almost assuredly a guarantee of affirmatively understanding how it's going to perform. There's no question about that. But the economics is something that is worth exploring from building to building, and can be really, really potent in a lot of cases.
I know with performance-based seismic design, I think insurance companies are starting to realize that lowers the risks on those structures. Is that at all a thought with this type of performance-based design? Is that maybe insurance companies will go, hey, look, this building's been designed. It's not kind of blanketed through the code. Is that at all a thought with this?
I really hope so. But currently, again, I'm not an expert on how the insurance industry is interpreting this, but there is an implicit assumption of adequate structural fire protection built into the code. There's a bias there. So think about how we design stairwells, because I'm a code consultant as well. The only thing that's regulated is the travel distance on a given floor to reach the entry door to the stairwell. So whether you're up on the 100th floor or the first floor, it doesn't matter. The code treats you as equally safe in the stairwell as if you would be in the street. There's an implicit bias that the structure is going to be fine, but that may not be the case. And there's been, although somewhat uncommon, there's been severe structural damage and collapses that have occurred. One Meridian Plaza, World Trade Center 1, 2, 5, and 7, Windsor Tower, the Delft University building, and others that highlight the benefit of doing the structural analysis for fire, because the vulnerabilities of those buildings would not be uncovered through furnace testing. Furnace testing entirely excludes connections. They're not at real scale. There's no continuity of the structure. It basically extracts the structure into individual components and then throws them back together with no analysis. So that sort of culture in the code of assuming the structure's fine under that extraordinary event, I think leads to a level of sort of comfort with not doing anything. But, I'd like to think that that's changing. And, that's one of the benefits of the Charles Pankow Foundation project is it's going to be released to the public in a few months. It's going to be completely free. And we strove for we want it to be replicable. So we showed all our calculations. We also want it to be fully transparent. We're talking about structural system limit states. We're not talking about mysticism. So that's an excellent question. I hope, the insurance industry will benefit, by understanding risk more, especially with buildings with a high consequence of failure, such as high-rise buildings. Because, the code would let you build to the moon with 2 hours fire resistance.
And this is aside from performance-based, but do you think there's room for the UL assemblies or the ASTM testing that we currently have, this 14 by 17 box? Like, will that be improved ever? Or is this just kind of a set deal for now?
Sure. So I mentioned that I have an affiliation with NIST, National Institute of Standards Technology. I'm on their expert panel for their state-of-the-art full-scale structural fire testing program. They've invested tens of millions of dollars to build this world-class facility where we can test full-scale structures. And even with a facility that is so far ahead of its time in terms of that facility, what we're bumping up against is the max that we can do is about 2 floors and about 1 full bay and then some partial bays.
Yeah.
So to be able to replicate a structure at real scale and to be able to account for all the coincidental structural design decisions using an empirical test becomes very difficult. And however, what is being done at NIST is just like the shake table tests of the past and present. It gives information to seismic designers to feel more comfortable that their analyses are validated. And that's what we're trying to do with structural fire as well.
So is there any standards that currently exist for the performance-based structural fire design?
Yeah, absolutely. So I mentioned that the American Society of Civil Engineers has really been a very good supporter of this. And the advancements made within ASCE have cultivated this. I don't think we wouldn't be anywhere where we're at, even in its infancy, without the support of ASCE. And so within the 2016 edition of ASCE 7, there's a new Chapter 1 section, 1.3.7, that basically, it's very short, and it basically says, thou shalt follow the code, or thou shalt do a performance-based structural fire design in accordance with Appendix E as contained herein. You flip over to Appendix E, and for the first time, it's in ASCE 7, it's in the 2016 edition, and we're actually balloting some updates to that for the 2022 edition. I sit on the General Requirements Subcommittee. So within that appendix, we provide skeletal requirements. So we don't want to prescribe what a structural engineer should do, because structural engineers are experts of stress and strain. We want it to be the same level of trust in their ability as seismic and wind. So we provide skeletal requirements there. And From my perspective, the experience and skills that are needed to really execute a performance-based structural fire design are within the grasp of structural engineers more than they probably realize. Because with your training as a structural engineer, you're really 90% there. I don't know many structural engineers that are experts on the weight of office furniture, for instance, but live loads have been, developed over time, and we use guides on how to account for them. Fire is no different. Structural engineers in some cases have to design for thermal expansion. If you're in a factory, we're just talking about bigger temperatures.
Yeah. So you mentioned before, like, it's all right if the structural engineer doesn't understand this stuff, right? Right now, it's not completely falling on us, but he says, like, who else is going to kind of push for this? This is a part of our industry. So do you see it as a responsibility of structural engineers to kind of make this happen, like bring this to normal design?
I've always sort of debated between the carrot or the stick.
Yeah.
I found that the carrot's a lot better, and it works a lot better. People like the carrot. So the carrot is, you don't need to do this. The code doesn't make you do this. If you hate fire, you want nothing to do with it, I'm cool with that.
Hey, we all hate fire.
I mean, like, if you hate designing for fire, we're all good with that. Okay. However, this is an aspect that structural engineers have been sort of outside the fray of. And not only is it probably one of the most unoptimized aspects of a building, it's ripe for innovation. And structural engineers are equipped to bring that innovation and bring that value to the table if you're willing to put in some more training to sort of bridge that 10%. A structural engineer coming out of school, and I'm certainly not, is not fully trained to execute a performance-based seismic design. It takes that continuous learning and that specialty and that interest to really go into that space, which can make you more competitive. We want this to be just another sort of way a structural engineer can make yourself special, differentiate yourself if it's something that you're interested in. We're trying to provide the infrastructure to work in a regulated, engineered environment, similar to performance-based seismic and wind.
Yeah. So let's say you got me, or whoever's listening is like, yes, I want to know more. I want into this. Like, I want this to be something I can do. Where do you start? Like, I know there's some resources, and many you've co-authored on performance-based seismic, or sorry, used to saying that, fire. Where do we go?
Sure. Yeah. And again, I'm going to preface this that I'm biased when I say this because I'm the editor of this.
Yeah.
And it's a product of the committee that I chaired for 5 years, the ASCE Fire Protection Committee. So as a companion guide to ASCE 7 Appendix E, ASCE has created manual practice number 138 entitled Structural Fire Engineering. And that's, and again, my name's on the front of it, but it's the product of many, many people, on the upwards of 50 people that have contributed to this. And it's rich in guidance. It's over 200 pages of pure performance-based structural fire knowledge. We tried to bring all of the best into one book. And professors are beginning to use that as part of their curriculum if they're teaching this. So again, I'm biased, but that is an excellent way to start. We wrote it in a way where we don't want to scare people away from it. We want people to be able, and also with I would invite structural engineers to read the Charles Pankow SEI exemplar designs report, which we spent 2 years developing. That comes out publicly in about 3 months or so. It's with ASCE Publications now. That basically, so the manual practice gives you all of the sort of raw data, the methodology, even heat transfer equations. The Charles Pankau report. So the Charles Pankau report was essentially funded by the Pankau Foundation and other agencies that contributed. They contributed about $250,000, and 4 structural engineering firms basically conducted hypothetical exemplar performance-based structural fire designs. And we examined the difference between the sort of unoptimized system and an optimized system in terms of its resilience and economy and carbon footprint. And that I feel will be a really good document for someone to really understand beginning to end, what would be expected of them if they were to go into this. And again, we want it to be replicable. We don't want this to be some black box where we want to bring people into the fold to do this.
One question that came up, you were talking about ASC 7, Appendix E. Does that still require peer review if you're to go that methodology?
That's an excellent question. So, and a very contemporary question, because we're balloting a new peer review section within Appendix E. So I've with help of my subcommittee, we have some draft language for peer review to be very similar to what it would be for performance-based seismic. Very similar wording, but we're changing, there's no ground motion. There's things about fuel load and heat transfer. If you go to the 2016 edition, there's commentary on it that a performance-based structural fire design is elective per the building authority. So the building authority has to be comfortable with the approach, and certainly having it within an ASCE document, an ANSI standard, will make them and has made them more comfortable. But they need to have the ability to review it, and they may want to have a third-party reviewer, which is definitely a good thing. And so peer review is in its commentary now, but we're trying to make it sort of an enforceable part of the method in the 2022 edition.
With this being so early on, have you seen jurisdictions accepting it, or have you gotten a good feel from jurisdictions on how they feel about this?
Yeah, so absolutely. So I've actually got a very notable jurisdiction to put on their letterhead, and the title of it, this letter, is Expectations of a Structural Fire Protection Variance. And they basically say, do it to the code, or we're only going to accept ASC 7 Appendix E. So it gives a sort of legitimacy to it. And I've had designs accepted in both coasts. But there's always, when a jurisdiction doesn't want to necessarily be the first one, they don't want to necessarily be the guinea pig, and it takes a lot of diplomatic work if you're dealing with a jurisdiction that hasn't dealt with this in the past, and that's certainly fair. But I think that as jurisdictions become more comfortable with it, they'll sort of transfer that trust in a similar way to the way they transfer trust to design a building for an earthquake. Trusting the licensure, which is rigorous, of a structural engineer to do the right thing. And within AAC 716, we provide minimum performance expectations, objectives that you must satisfy. So we sort of set a backstop, and we also give the building authority the infrastructure by which to implement discretionary objectives. So design for burnout with no collapse or other objectives.
Well, thanks so much for joining us. We really enjoyed having you, and we look forward to having you again.
Thank you. Yeah, I'd love to.